So, question 2, part B, I added a hint to make it nicer for you, but I forgot to upload the version with the hint in it. So, thank you very much for Patrick and Ashley for pointing out my stupidity. So, I've now uploaded the correct one, and there's a hint for part B to help you get started on that. Just in case you're having any difficulty with that. If you've done it without the hint, good on you. But I've added a hint in. So you have an assignment due this Friday at 5 p.m. Hopefully, as always, this isn't too much of a surprise for you. I will have a consulting session from 10 till 11 on Friday in my office if you need help. If you can't make that time and you still desperately need help, then send me an email or contact me via Slack and we can arrange a time to meet. That should be fine. So, that's not Lois Mars, that's not what I want. God, lasso, that's better. I'm writing the 4 lines lecture. So, we had this idea of a ridge regression. So we've been looking at saying, well, can we start to somehow select a better model that we started off with? And we'd had subset selection, forward, backwards, algorithms to basically look at putting predictors in and out and finding the best model. Where best is usually under something that approximates the test mean square error. So we can either get that by estimates using cross-validation, or we can use some sort of metric like AIC, BIC, Marlowe CP to represent it. Then we looked at the idea of a ridge regression. So ridge regression, you're trying to choose the parameters that will minimize the residual sum of squares, but we added a constraint. Our constraint was we had a tuning parameter, lambda, which is greater than or equal to 0. And we basically took all the coefficients, squared them, add them all up, and that was a measure of sort of our coefficient space that we were looking at. So what we're going to do today is we're going to do another one which is very related to that called the lasso. So the key concept is in ridge regression, the coefficients are shrunk towards 0, but it often doesn't set them to 0. Sometimes you really want to go, look, you're 0.0001. Why don't we call it quits and call you 0? Because at this point, all the predictors are still in there, they're just not having a lot of an effect on the prediction in the model. And that's what lasso allows us to do. So, here's how we're going to do it. First of all, you've got the first term, that summation as I goes from 1 to n, yi minus b to 0 minus the sum as j goes from 1 to p, b to j, xij. That is the difference between my model and my observed value. I square it and add them all up, so that's my residual sum of squares. Then I add a penalty term. My penalty term is now, we still have a tuning parameter, lambda. I've got greater than 0. It could be greater than or equal to 0. I didn't get my inequality right there, sorry. Notice, first of all, that my j goes from 1 to p. Again, I'm not touching the intercept. I'm only looking at the rest of the coefficients. And what I'm doing is I'm taking the absolute value of all the coefficients and adding them up. So before, I squared them and add them up. This time I'm taking the absolute value and adding them up. And this is called the lasso regression. Do you have that written down? So I'll wait.
No, it's alright.
You sure?
Yeah,
So we're going to talk about norms. Basically, the ridge is based on what we call an L2 norm. It's actually on the square of the L2 norm. So there's proper L2 norm. In fact, a P norm is I'm going to take some variables, I'm going to raise them to the Pth power, I'm going to add them all up, and then I'm going to take the Pth square root, the Pth root, basically. So you've got your L1 and your L2 norm. So what this is if I took a vector and I took the L2 norm, I would take each individual element, square them, add them all up, take the square root. Well, in lasso, I'm now doing an L1 norm, which is basically for any vector, is I take the absolute value of every element, add them all up. So they're just, I know it's not quite right, but they're a sort of length of that vector. There's one way of thinking. One is the length in Euclidean space, one's under this absolute space. So the lasso shrinks the coefficient estimates towards 0, and if lambda is sufficiently large, it will set some to 0. So as this extra advantage, it doesn't just get small, it eventually goes, you're going to be set to 0. So it's acting as a model selection process for us. So let's have an example, and then we'll start to explore it. So we're going to go back to my favourite subject, baseball, because we know I know baseball. I believe it has a base and a ball. So this is the Bowen data set for the book, which is called The Hitters. And what we're really interested in this data is to be able to predict the salary of these baseball players given various summary statistics for them. So summary statistics are, for example, how many times they hit runs, etc., how many runs, how many walks they did, how many years they've been in the industry. So, first of all, unfortunately, remember that the function we use to do ridge regression and also lasso regression doesn't take the formula way of describing your model. Most of the functions you see usually will have a response variable, a tilde, your predictors. This doesn't. This, you actually have to give it your design matrix without the intercept, really tricky, and you have to give it your vector observed response variables separately. I have been looking, there is, you know how there's the tidyverse? I discovered this weekend there's also tidy models. There's a whole set of packages in development that are trying to make it much more complete when it comes to all these models, so they all take this similar form. I would tell you all about it if I'd had a chance to read it all, but I'm still working slowly through it. But there is people trying to get all these standard machine learning methods to be similar. So every time you get a new one, you don't have to learn a new way of getting your data into it. But until that gets sorted, unfortunately, we're going to have to get our X. So I need the model matrix. To cheat, I do the design matrix by using the model matrix. I give the formula salary tilde dot. So we're going to take salary on everything else, data equals hitters. That will give me automatically an intercept. So I get rid of the intercept, which is the first column. Because with all of these, they are, oh no, the league and division does actually have categorical variables. I was going to say, it'd be pretty right if I look straight from the data table, but because we've got categorical, I couldn't. So, how do we do it? We use the glmnet command again. I give my x, my y, and then alpha. Remember when we did ridge, alpha was 0. Now to do lasso, we do alpha equals 1. It seems backwards to me, and it's because it's doing actually a weighted. You can actually do a weighted between the lasso and the ridge, and it's the amount of weighting you're doing. I just give that.
So you can do like 0.5.
Yeah.
You can do
Yeah, absolutely. So here you're doing the absolute weighting, so you ended up with the lasso. So you can do a weighting between them. Because it seemed to me wrong, I don't know why. I thought in my head that it should have been the way around, I don't know why. So what I've done this time is I've fitted my model and now I go plot. And it gives you this very nice plot. It gives you the L1 norm, which is why I mentioned it. And you notice, roughly, you can see you get all these coefficients. And as you basically add more penalties, as you add more lambda, they shrink down until they all disappear eventually. So before they would have sort of slowly shrunk down, but here you can see that they pretty well go along and then bang, they go straight into the 0. And towards the end of the lecture, I'll show an illustration of why this is happening. Okay?
What are those numbers at the top? The 0, 6, 6, 7?
Degrees of freedom.
Okay.
I haven't had a chance to look, actually that's not a question. I can't remember if they're effective degrees of freedom or degrees of freedom.
Okay.
I haven't discussed effective degrees of freedom. When we get to smoothing splines in a couple of weeks, I'm actually going to go through what effective degrees of freedom are.
And the different color lines there?
They represent different coefficients in your model.
Okay.
So it's the value of the coefficients. So what we're seeing here, for example, this green one, that's going along, and then it gets shrunk and shrunk, and then it hits 0. So this is as you change your parameter, how your coefficients change. So the first thing you should ask is, well, how do we choose lambda? What value should we choose? Well, again, cross-validation is built in, so we may as well use it. So here, I've used the cross-validation of GLMNet. I've got my X, which is my predictors. I've got my Y, which is what's variable. I've got my alpha set to 1, because I want lasso. But just to remind you of what it's doing, it's going to take some of your data, put it aside, fit your model on the rest, then go and predict the data, get a measure of how good your prediction is, and just keep doing that. It's then going to do that for a whole range of lambdas, and then it's going to give you an indication of which lambda minimizes your cross-validation error. In other words, which lambda is minimizing your test mean square error. Yep. Then this returns an object. From the object, we can get the lambda.min, which is the one that gives the smallest value. And then once you've got that, in this case, lambda was 0.961107. So once you've got your lambda, you can actually go and use that. The other thing you can do is you can get your plot, and what this does is it gives you your mean square error for different values of, in this case, log lambda, with nice confidence intervals. Again, the ones at the top are your degrees of freedom. Interestingly, I discovered this week, is you get your minimum value, which is about here. Remember, it was 0.96. So it's just here. You can actually get an extra thing out of it, which says, can you find a lambda that is smaller than the one you've got, but it's within a standard error of the other one? So it's saying, you're not going to get the best lambda, but we get a close enough lambda, but a lambda that would actually give you a slightly smaller model. So you can actually do that as well, which is quite nice. It's called the Wonst SE you can get out. In this case, I'm not that worried. And what I've done here is I said, well, look, I'm going to take that best lambda, because it won't work out every single lambda, it sort of calculates it by interpolation. So I said, for the S, but predict for me, using the model, what the coefficients would be for that. Give me the first 20 coefficients, which is all the coefficients we had in this model. And then all I've done is I've taken these. You might wonder why I've done that 120, why not just grab it? Because when you do the predictive, it turns it as a sparse matrix, which isn't as nice. So by asking for the first 20 rows, it coerces it into a standard matrix. In fact, it coerces it into a vector. But then you take all these, and I said, just grab the ones that are on 0, and you can see it's automatically reduced it down. So it's done model selection for us automatically. We didn't have to do all that faffing around. We just chose that lambda, and it's by doing that, it's found the one that minimized the test mean square error, and it's done subsetting for us, model selection for us automatically, which is really nice. Lasso is used a lot if any of you are doing sort of GWAS, which is looking at genotypes and prediction. They use lasso a lot to get this down, get the number of genes down quickly. Okay, so let's have a think about some alternative formulations and why this is doing what it's doing. So if you think about ridge regression, you're going to go back to ridge regression, you can actually consider this as a constraint problem, where in this case your heuristic you're interested in is choosing the values of beta that minimize the heuristic on the left, which is our residual sum of squares. So if you think in optimization terms, you're trying to minimize your residual sum of squares subject to, or what's your subject to? Subject to that the variables that you can actually adjust, that the sum of the squared of them is less than or equal to sum s. So it's just an optimization problem. It's a constrained optimization problem. So what would be the equivalent for lasso? Well, it's very similar. You're trying to minimize your residual sum of squares, but now your constraints are subject to that the sum of the absolute values are less than or equal to s. So let's have a look at a picture. Let's assume we've got the case where we've only got two predictors. Then what are the ridge coefficients? What we're trying to do is we're trying to find the smallest residual sum of squares. So we want to find a set of coefficients that give the smallest value, but are contained within the circle around the origin of beta 1 squared plus beta 2 squared is less than or equal to s. That's what that constraint is doing. It's saying, look, explore this space, find me a point in this two-dimensional space such that it gives you the smallest value residual sum of squares, but it's also contained within a circle around the origin. What about the lasso? Well, this is going to be a diamond. A diamond defined by the absolute value of B1 plus the absolute value of B2 is less than or equal to S. So one does a circle, and one just does this nice little diamond. What about subset selection? Well, subset selection would be, imagine we said, I want you to have P predictors. It would be in this format, minimize the residual sum of squares, subject that the number of predictors, so I here is an indicator, is counting the number of coefficients I haven't set to 0. So the total number of non-zero coefficients is less than some equal to S. So you're basically saying you can have up to S predictors, find your best model. And in fact, to some extent, this is what we'd really like to do. We'd like to say, look, you've got so many predictors, go and find the best model. But this is, we know, is computationally hard. While your ridge in your lasso gets to this indirectly and is fast. So when does a lasso give you 0 coefficients? Well, here is my illustration. What we've got here is, first of all, your beta hat, the dots, are the true value of your coefficients, beta 1 and beta 2, that would give you your smallest residual sum of squares. So that's absolute truth. That's the one that we absolutely want, but we're adding these constraints. We've got a constraint problem. Now, first of all, if my circle and my diamond were large enough, i.e. lambda was small enough, it would just return the beta hat and the beta hat. You're basically saying, find me that dot as long as it's contained within, and my circle's now big enough to have the whole region, so it gives me that dot. But what happens is, as I get my parameter going up, these things start to shrink down. So now what we have to do is we say, find me the point that lies in the blue square that gives me the smallest beta hat. Now what them ellipses are, is they're the mean, the residual sum of squares. So if you think about the one on the right, which is the ridge regression, you'll find that you basically want to find your ellipse that just touches that circle. That point there, where the red line and the blue line meet, is going to be your smallest residual sum of squares by the red line, and it's where it's just contained within that blue circle. So that's going to be the point you'd return. And because it's a circle, there's no real sort of pushing it towards a corner at all. But soon, you've got a diamond. You find that more often than not, it's going to hit one of the corners first. And what's a corner? A corner now is one of the coefficients equaling to 0. Now, if you do this in n dimensions, you have to think about more complicated diamonds, but that's the key concept, is that with your L1 norm, you're more likely, when you're trying to find the point that's within that blue region and minimizes your residual sum of squares, it's more likely to hit a corner, while there's not as many corners on circles, or there's lots of corners, depending on how you want to look at it. So that's the intuitive illustration of why it gives you more 0 coefficients with the lasso compared with the ridge. I'm going to illustrate it in another case, but I think in a very special case, illustrate the ridge and lasso. So, let's assume we have n observations and p parameters. Yeah? And so, in our case, our design matrix is just going to be an identity. We're basically saying we've got one predictor for every observation. So it's a bit of a degenerate case. We're also going to simplify it more by, we're going to fit a no intercept model. So we don't have an intercept, we just basically have a parameter. And what we do is choose the parameters such that the distance between our parameters and our yj's is minimized. So in this case, we've got yj minus beta j. So we've got a really simple, there's no predictors or anything. To some extent, if you look at that problem, you could solve it, but you're saying, well, the best bet for beta j should be yj. Make sense? If you differentiated that, put it equal to 0, you should get p equations such that your best guess of beta j hat is just yj. Okay, so we've got a really degenerate problem, but I'm using it to illustrate a point. Well, we can now take that problem, we could do our ridge regression. And if you did, I haven't done it here, I thought I'd leave it for an exam. You can see that your best estimate of beta j hat is you take your yj and you divide it over 1 plus lambda. Okay? What about the equivalent with the lasso? Again, I've left that for later. But you find that the solution now is that bj equals yj minus lambda over 2, if yj is greater than lambda over 2, or plus if it's less than, that's not right. Yeah. That's a minus, that 0 is a minus there, I do apologise. And then 0 if it's contained. Which is a complicated way of saying this diagram. So let's go through this diagram and think about it. So, first of all, look at the green line. The green line says what would be, so on my x-axis is the observed value, and on the y-axis will be my appropriate coefficient for that one. So what he's saying is, for example, if my observed value of y was -1, then my coefficient associated with that y would be -1. So that green line is just the y equals x, although in this case it's beta hat and y. Okay, so what does the ridge regression do? All the ridge regression does is instead of having a slope of 1, it's now got a slope that's just been adjusted down. It shrinks everything down a little bit, but it shrinks everything down by the same amount, proportionally. So you can see with the blue line, everything's been shrunk towards 0 that little bit, but all with the same proportion. So what does the red line do? The red line is lasso. And you can see that, to some extent, anything that's outside 0.5 or less than -0.5 gets left alone. But once you get within that region, once you get close enough to 0, bang, you get whacked to 0. So the ridge just takes your normal estimates and adjusts them slightly. I mean, this is a very degenerate, obvious built-up example. While your lasso says, I will adjust them, but once you get within a certain range, you just get wiped to 0. That's roughly what lasso's doing. You sort of saw it on the very first plot. You saw values going along, and then the lambda got enough, and then bang, they all got wiped out. Which goes right back to the thing at the start where I said, if you're close enough to 0, let's just set it to 0. I don't want coefficients of 0.001. It's almost like it's the very fancy equivalent of just rounding it. But don't just round it. So let's have a look at in the last and final interpretation. So we're going to have a look at a Bayesian interpretation. So let's remind ourselves about Bayesian. So up on the slide there, what we really care about is we're going to say, well, look, we have X, which is our predictors. We have Y, which is our observed data. And we have some betas that describe the relationship. Okay. So the thing to the proportional to on the left is F beta, then you've got the pipeline there, the vertical line, X, Y. So let's read what it says. That says, what is the posterior distribution of my betas given my observed value of Y and my predictors. Okay. So that's the distribution. Remember, we're now in the Bayesian world, so instead of having these parameters that are fixed but unknown, they now have distributions. And the posterior distribution says, how would you describe the possible values and the probability of the possible values after you've looked at the data, hence posterior. Now, we can write that as the likelihood. So that's Fy given x and beta. So that is the relationship between our y given our x and our betas, and our prior distribution, i.e. our belief about the distribution of beta before we get any data, which we denote by f of beta. So the standard thing is you have a prior belief, you multiply it by your likelihood, which relates your data to your parameters, and through that you then get your posterior belief about the parameters. So you go from prior to posterior through the likelihood. We're also going to assume that our prior distribution is such that all the betas have some functional form and they're independent of one another, so I can just multiply them all together to get my joint distribution on my betas. Okay. Okay, let's make some assumptions. If we assume that the prior of the beta is a normal distribution, seems to start with a mean of 0 and a standard deviation that's a function of lambda, then the posterior mode of mean of beta is given by the ridge regression solutions. So if I start with this Bayesian and I assume that my belief about the betas before I do anything, that they're all individually normally distributed, and I go and do the calculation and I get my posterior. My posterior, if you looked at the mode, which is the highest value of your PDF, or the mean, which is your average value, that would be equal to what we'd get if we did our ridge regression. Okay? What about the lasso? Well, here we need something a bit different. Probably the first time you see it, we're going to get a double exponential, which is also called a Laplace distribution. Still has a mean of 0 and it has a scale parameter this time. So before we had that our variance was some function of lambda. Now we've got our scale parameter as a function of lambda. Now the posterior mode of beta is equal to the lasso regression solution. The main reason is that before we had both the mode and the mean was just that because you took normals, you put it through a normal, you get normals, and with the normal distribution, the mode and the mean are the same. This isn't such a nice little thing, but luckily the mode is still given. These are such lovely little proofs, I decided I wouldn't wait for the exam. I'll put them in the assignment. You don't want to cut this off. It's fun. You want to get straight into it.
We have to wait another week for that to come out.
Oh, I'm sorry. Well, not a whole week. It'll be out on
Oh, sorry, 4 days. I mean, it's still too
Friday. I can get it out early if you want.
Fine, don't worry about it. Don't mess yourself.
It's very good of you. You all give. Just in case people don't know, here is my normal distribution, the nice bell-shaped curve in blue. Well, there's your Laplace. You can see it's basically it's very pointy around 0. It's the best way of describing it. It's an exponential distribution, but it's a flipped exponential distribution or Laplace distribution.
So it hits x equals 0. So it hits the y-axis. It's not asymptotic.
No, it will drift off. It doesn't.
I'm sorry. It hits the y-axis at x equals 0, or is it asymptotic?
I think it's pretty well asymptotic, and I think it's sort of saying it's there. I think if you actually plotted it, there's a little tiny missing bit there. It's continuous, but it's not actually present. So, a nice short lecture. Don't worry, we'll get back to long ones soon, but I thought I'd stop there before we start the next bit. Any questions on that at all?
Why is it called lasso?
Good question.
Lassoing them and setting them free.
Yeah.
Yeah.
Oh, okay.
It will be something as daft as that. Remember, statisticians don't have a big social life, and they think that, let's face it, we thought Magritte art was hilariously funny because it was about, Belgian surrealist art.
Wait, so what's the joke behind Magritte?
You don't know the...
Oh, that's nice. I wonder if anyone who doesn't know the Magritte art.
Okay, so this is Magritte. Magritte was a Belgian surrealist, and he did this picture, which says, "See, pass, pipe. This is not a pipe." So surrealism is about, breaking down your concept of. So this is not a pipe, but obviously it's a picture of a pipe. In Unix, you have a straight line, which is a pipe, which will join two things.
Yeah.
So they have something, the percent greater percent, which is a pipe, but it's not a pipe.
Oh.
Hence it's called a Magritte R. It's brilliant. I love it.
Also, Lasso stands for least absolute shrinkage and selection operator.
Oh, so
Sounds very forced to me.
Oh,
It is very forced.
Yeah, it's like the Pastor theorem from RB. It's very forced.
You wait till we do, the week after next, we're going to do Mars. And Mars, basically, you can't use the package because you have to pay. So the one that's in R is called Earth. And they actually have an acronym, and they call it a blah, 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 but they must have just we call it this so we don't get sued. So, yeah. So we will do Mars. But we won't do Mars, we will do Earth, because Earth is what you do when you go from Mars to R. Cool. Any questions at all? Remember, if you have any questions about the assignment, come and see me. If not, I will see you all on Wednesday. There is no workshop this week, and then the workshop a week on Friday as we start looking at data table. Remember, there's a hint for the assignment in the assignment now. I do apologise I didn't have that up. I hope none of you spent a lot of time trying to get that one to work. Cool, that's it. Thank you very much.
Still looking from your slides. Your graph of the lambda values. So